Uh, I'll finish to write the title in a moment. Uh, First, I would like to thank you very much for the opportunity to come here. The first time I came to Miami was in May, from the last conference that was held here. And in this idea, I always start from that conference. And I must recall that on that time, we started to think about some physical concepts for exotic manifolds. Because all in all, I have been always interested on these exotic manifolds, especially because they are not homogeneous space. So they could not fit good physical models somehow. And it seems that we can also realize something, of course, in a much deeper level than myself, in his paper on 87, when he discusses the possibility of a differentiable and distinguished exotic structures on 10-dimensional spheres be related to some supergravity stuff back in the days. So since it's Friday, we are probably very tired. I'm gonna try to keep this very dynamics and of course trying to put the motivation instead of furnishing a lot of details that just can get us more tired than expected. All in all, my talk is about the generalized logarithmic transformation and its manifestation through exotic methods. This is a natural continuation of Lino's talk and is a work in progress with Professor Ludmil and Professor Lino. Okay. So Lino was talking about these constructions of spherical duality and these kind of cross diagrams that appeared to us. So it all became very well known about these star diagrams when people realized they needed to different tools to understand different geometric data. For instance, if we look to this quantum field theory and we start to play with some model, usually you are assuming somehow that there is an inherited smooth structure on your bundle and your connection and this kind of stuff. And then perhaps we never, or the physicists at the time never thought about what kind of structure can perceive different manifestations of physics, looking only from the point of view of manifolds. Because when we start to making Riemannian geometry or gauge theory, we have to have some magnitude and some connection. But the point is that at first there is some logical step there that it's presumably to have a smooth structure, fix it. So when we try to begin working with connections and metrics, there's usually at first a smooth structure that's fixed. Somehow here we always try to see, can we get same results for different kind of smooth structures on the same homeomorphic manifold? Okay, and this is more or less the spirit of the thing. And to the point of view, when Euler in 56 discovered these exotic manifolds, it was questioned a lot whether these manifolds admitted similar geometries to classical spheres. Okay, because classical spheres are a great example of manifolds with positive sectional curvature. Okay, so would that be true that these exotic spheres admit symmetrics? And the answer is that still nowadays we don't know. This is an open problem in Riemann geometry. In spite has been a lot of effort trying to fulfill this misunderstanding, perhaps, of how geometric manifestations appears on the same topological level. Because when you look to this Riemannian geometry, classical theorems such as Bonnet-Meyer's theorem, Prisman theorem, and so on, and even Gauss-Bonnet theorem, presumably all the constraints that appear relating geometry are only at the level of point set topology, not on the level of smooth topology. But then Hitchens, perhaps let me in the 70s, using spinors, he showed that there are some exotic spheres in dimension 10 that do not admit even metrics of positive scalar curvature. So the weakest form of curvature would not be achieved by some exotic spheres in dimension 7. And this is constrained by whether or not it can be realized as a boundary of an 11-dimensional spin manifold. So all in all starts just like this. But then somebody trying to solve this question about the existence of positive or non-negative curvature on exotic spheres. Here comes this example of Grama and Mayer that shows there's an exotic sphere with a method of non-negative sectional curvature. And this is achieved only by looking to the induced metric by Riemannian submersion. So what they do is that they take the video SP2 and they get fit everything like we can have using that star diagrams. But this is, although this is modern language, more or less the spirit of drawing binary construction is that they can realize some bundle here with total space SP2 that has no negative sectional curvature on a bi-invariant metric, because this is a compact Lie group with a distinguished S3 action here that uses quotient this 7-dimensional exotic manifold. So since the Riemannian submersions, as we learned in the Riemannian geometry class, do not decrease curvature, the quotient has a metric of non-negative sectional curvature. But interesting enough is that if I do recall to you, if we denote by this Q here, the bi-invariant metric, then we can produce a metric here that will just denote by G prime. And the sectional curvature of this G prime is precisely the sectional curvature of Q restricted to these horizontal planes that will just denote by, because this is a submersion, so here we can identify the vector space on the basis by this H prime. That's the complement of the fibers here. So all in all, the sectional curvature of the basis is the G prime that is related to the curvature of the total space plus something. And this something here, this connection form, will be related as also with will be related to some Chinese science theoretical aspects of the duality that we are handling. So let me push this one. So this is more or less the spirit of this kind of diagrams. Grama and Mayer introduced the first with a different language of these diagrams because Riemannian submersions do not decrease sectional curvature. So aiming to produce manifolds with non-negative sectional curvature would be great if we could produce this as quotient for some Riemannian submersions. But then I told you that heating tells that some exotic manifolds cannot be built, cannot admit metrics of positive scalar curvature. So naturally, we're tempted to think that we cannot never put some of the heating constructions of the exotic spheres as base for Riemannian submersions when the total space has non-negative sectional curvature. So they naturally do not admit construction as quotients for some compact Lie groups, of course. Otherwise, it would not be possible to obtain such a result about this non-existence of positive scalar curvature. So somehow the possible constructions of these manifolds that fit in a star diagram should be constrained in a more specific way that should take into account Hitchings examples. Okay, and Duran and Higas, Higas is a Greek mathematician and Duran is a Venezuelan mathematician. They both live in Brazil. They made, and still they live in Brazil yet, but they made a very prolific and quite philosophical work in trying to standardize these things. And they invented the concept of autophagia. The point is that the manifolds that can be described in this language of star diagrams that satisfy some property of autophagia, or at some point they named this also as a re-entrance procedure. Because what happens here is that the manifolds that they could build could be built by this plumbing or straightened angle procedures. And to quantify this, they use this term that they refer to autophagia that you recall from Lino's talk. Then we have this P3 SO4. This is Z plus Z. And just as Lino showed, we have these maps. We take some X here from S3, and then this of course a map that takes 8 to 8. Okay, and then these maps act like D and X. We take this V, and this is X plus V. Sorry, X to the power n, V, X to the power n. We have these classifications of the bundles, and the concept of autophagia or reinforcement procedure that they're mentioning is that because this map here, the adjoint map that you can think as a hat from S3 and S3 to S3 and S3. It's just yeah, it's S3 to S3, and we get some X, and then send it to E and N. Apply to X. Yes, so this autophagy, the coupling of these terms are more or less quantified in the sense that they all fit on this kind of diagram, if and only if they need some autophagy construction that is equivariant with respect to some term. And all in all, when you look to this kind of diagram, it's very important to stress that we can compare geometries in a very elegant and simple way, in the sense that geometric constraints here in the terms of curvatures can be transferred or transported to constraints here. For instance, matrices with positive ridge curvature can be taken from here to here and vice versa. So looking from this classical perspective of a Riemannian geometry, everything is comparable. But why not sectional curvature? Because of this distinguished term here that is related to the Schoenstein's form on this kind of duality. So all in all, this is more or less the spirit of these star diagrams. They allow us to compare different geometries. For instance, on the top on A, we have shown that if this manifold here admits a Lorentzian globally time-oriented metric, then the complete physical dynamics from this manifold is the same, can be made the same as here, even in the topological matter, in the sense that time-like geodesics is complete on one manifold if it's complete on the other, and vice versa. Okay, so this is the spirit of this kind of things. And this led us to think, well, if we can transport Riemannian geometry level information, can we transport topological level information? In the sense, can we produce some kind of duality in some sense? And then it suddenly appeared that the work of Matai, Ludmil, Nestle, and just as Lino pointed out, this manifold here, S7, it can be made dual in the sense of spherical duality, because they are also total space of some spherical bundles as this sigma 7 homotopy sphere. So if we take here some class, let's say J, where J is class J here is an element of A7 that can be identified with this H4. Then we have a diagram like this. Let me put just M here. We have this M along to the. This is also M4. So Lino showed that these two manifolds are dual in the sense of Matai over this S form. And then we have this correspondence space as well. But what I'm going to discuss to you is that this duality can be realized by some kind of generalization of logarithmic transformation. So not only duality can be made in terms of star diagrams, but star diagrams are related to what we shall call to be a generalized logarithmic transformations, usually appear in the elliptic fibration scenario. So the point is that we can teach everything like here. Well, that's one. This is the spirit. The spherical T-duality can also be realized by this kind of logarithmic transformations that I will recall to you. Now, what is this? And looking for elliptic fibration scales, and why can we get this kind of generalization? And this logarithmic transformation procedure that we shall describe here, it's purely topological in the sense of autophagia that we just mentioned. So it is only related with topological aspect, but it gains its physical and its geometric manifestation through the ways of looking for the possible actions and possible representations of actions that we get. I recall to you that if you have some elliptic vibration here, let's look to this elliptic vibration. Then following the work of Dom, if we take some regular fiber, F, regular fiber, fine. Then what's called as a logarithmic transformation, that a logarithmic transformation around the fiber is a choice of orientation reversing diffeomorphism from a tubular neighborhood of the boundary of the tubular neighborhood of this fiber that can be identified with 2 times this orientation. So here it should be orientation reversing diffeomorphism. So we take a logarithmic transformation around that is an orientation reversing diffeomorphism such that we can take off this, we consider the manifold here, so we get X, then we take off this part, and then we glue with this glue, and this one, sorry. This never works. You can lift in your own stuff. And then we glue to the common boundary. So this can be thought as the classical logarithmic transformation procedure.
What is the data? A matrix, an integer matrix, so what is the data here?
Yeah, here is also, whenever you do this kind of procedure in this scenario, what we get is that making logarithmic transformation is completely determined by the degree of this map pi here. So, for instance, in this case, you can always think of pi as an element of SL3. Okay, so let me just use this star subindex because it's the map at the level of fundamental group. Okay, so this is a possible analysis of this logarithmic transformation, but let me give you some different perspective of this, and you can see it in a slightly different manner. For instance, we have this the coupling of disks and everything. So I claim to you, and we can show this by relying on the local structures of elliptic vibrations that we can write down precisely this here. So we're taking off this. So I claim the following. Let me just claim here. Every total space of some elliptic federation can be described by a straightened angle procedure. So we can write down this just as x, we can decompose it as d2 times the 2 to right. Fluid, by some diffeomorphism with a common boundary with another top of this. Okay. This is the total space of any elliptic fibration. Okay, this is the total space. And then what is a logarithmic transformation? It's just that we make it something like this. So classical logarithmic transformation can be seen as take d2 times d2, and then we write down this here, d2 times d2, and then another top of this, d2 times d2, d2. Okay. So our manifold, it can be obtained by, we take the straightened angle procedure here through a common boundary that you're going to put here in the middle. So we have this S1 times D2 times D2 times S1. So denoting the inclusions here by I0 or infinity, performing a logarithmic transformation over one fiber, around one fiber, is equivalent to choosing some psi 0 here or some psi infinity here.
That's 6 circles, isn't it?
Exactly, precisely. Yeah. And then the gluing, the corresponding gluing is just psi 0 minus 1 is 5.
So everything is happening in Excel 6Z.
Yeah, exactly. If we perform two logarithmic transformations, like one in each fiber, if we perform this only around one fiber, then we can reduce.
But you're not losing identity. I'm saying that the universe is self.
Perfect. Yeah. And I just wanted to write down this because then to answer you about this as help is that we can functionalize this to the fundamental group level. In the sense that what we shall get is erase here to keep at this minimum. So we can functionalize this whole diagram, and then you shall see how everything is decoupled. Is that because functionalizing that we just mark this as A?
A tiny question. So the inclusions are, I cannot understand this. You have 6 circles with that. You're seeing.
Yeah, because
What's in
sorry. It's just one. Sorry. Yeah,
right?
good one. Yeah, good one. Sorry, very sorry. Yeah, you're correct. It's just this one. That's it. Very sorry. Yeah.
Okay.
I was just thinking on the product of two elliptic fibrations. Very sorry. Yeah, thank you. Great observation. Yeah. The common boundary has just the SMP. Yeah, it's a very nice. Yes, SMP. Yeah, sorry. Very sorry. Yeah. I just confused the boundaries. It shouldn't have that. Because after this, we are going to take the product of two elliptic fibrations and then it will.
It's the same.
Exactly. Yeah. Yes. The common boundary is for all of these, and then we have just natural inclusions. And then what we are doing is that instead of making natural inclusions, we are choosing some reversing orientation geometries. And then the new manifold obtained from straightening angle is given by this composition. So this is logarithmic transformation at the purely topological level. But functorializing, let's say, functorializing, I'm not sure if this is a term. Like I1, what we get is that we have I1, the fundamental group of this D2 times. And then here, we take the free product and the amalgamation here. Start the map at the fundamental group level. We have I1, D2 and D2. And then we have this I0, I1, S1 times Then times the oops. Zero. D1. D2. That's D2. Y1. D2. And of course, then the corresponding fundamental group of the manifold that you perform the logarithmic transformation is obtained by well. We take these two parts here, and then we make the amalgamation product. But now making this line. Oh, sorry. No. Then we'll take. So this is the functorial aspect of this, of everything. How now classical logarithmic transformations can be obtained by strengthened number procedure. And two elliptic formation on different fibers are encoded either by sine zero or sine infinity. And we can fluctualize everything to the fundamental group level and what is previously straight angle or plumbing can be transported to this kind of amalgamation product at the fundamental group level. So this is a topological only observation of this kind of logarithmic transformation. And what we can do here is try to generalize it to higher models. For instance, to try to apply this to the kind of duality that we have proposed. So all in all, we for a moment shall forget that this is some less restricted to elliptic vibrations and only think about the disk, the composition of classical and exotic spheres. So what we shall have here is that the analogous of generalized logarithmic transformation that we shall propose is just let's change ingredients. So suppose that we have a manifold. In the context of a spherical duality, what we shall have is a manifold M that can be decomposed as in the 7-dimensional case, for instance, just to be easier, we have this S3 times D4 joined by some function here, and then D4 times S3, and then a generalized log transform should be something at the level of diagrams, just like, well, we have this S3 times D4, and then we have this inclusion as 0, and the common boundary is just S3 times S3, infinity, and then D4 times S3, and then generalized logarithmic transformation just draws now sine 0 and sine infinity. That gives this D4 times S3. S3 times D4. This is the definition of our generalized logarithmic transformation. If we perform this on two fibers, then it's a choice of non-identical or non-inclusion. So this psi 0 has to be not isotopic to this I 0. This will produce a non-standard logarithmic transformation. So it fits in a diagram like this, and a good way to write it. Since when we write a diagram like this, then we can try to apply this to another concept of functorial aspect to the category level, and then try to understand the manifestation of logarithmic transformation. So let me just show to you very quickly how then the lunar sphere can, an exotic sphere versus the Grama exotic sphere can be obtained from a logarithmic transformation from this manifold. Well, if S7 is nothing but, okay, first and then here I have the blue, so F, and then I shall have the sine 0 minus 1, and okay. So S7 here is just S3 times D4 fluid by this F D1 0 D4 times 3, where this f T10 is just the x g. This is not from x in g T10 x, where I will call you that T10 x. If we take some v from the quaternions, this is just x. So a manifold, the seventh sphere can be written in this manner, and then the Grama sphere that I will just denote by this is just S3 times D4, and it's just D2 minus 1, D4 and S3. So a logarithmic transformation that generates this sigma 7 from this S7 can be obtained just by taking this psi 0, let us just take it to be the analogous or some isotopy of psi 0. And then this psi infinity must be such that this f.
I'm a bit confused.
Yeah, okay.
Once you do this matrix thing, the choices actually matter to really get the smooth structure and everything.
Yeah, they do.
The choice, and then you really write logarithms.
Exactly. I did the level of functions, yeah.
Not just topologic to choose anything, I have to choose the right thing.
Exactly. It really depends. For instance, here to build this sigma 7, we must bring this part and change it. This is a possible constraint.
Not only that, I mean, when you say the common boundary or anything, I cannot just attract that thing there.
Yeah, no. You mean you have to pick a specific common boundary to do the gluing.
Right, smooth.
Yeah.
Version of the mapping into exponentials and logarithms and things.
Precisely, you have to do this.
Really get sigma 7, something like that.
Exactly. The point is that if you have a diffeomorphism on the boundary that would naturally extend to a diffeomorphism of the more or less 3 times before, then the resulting structure should be the canonical. So the construction has to be made such that you are not allowed to extend the diffeomorphism to the whole disk. Just in a sense that is. Yeah, that is the point. Okay, you cannot just.
But that's just topological. Sorry, just. But you still need to write an honest smooth map here. Yeah.
Yeah, no, I see your point. And let me just see if I'm understanding correctly, because you're thinking of the level of matrices.
Yeah, you have this data, but there's a little bit more, isn't it? If I just took this fractal common boundary, I could still write something there, that is smooth, but the embedding is matter or doesn't matter.
I see your point. Like, it's not an arbitrary kind of just decompose and just try to put. Yes, precisely. And this is the key point. Whenever we write, for instance, we could just write this M7 as 2 disks 7.
But this could be very complicated.
Could be combinatorically very complicated. Yeah. For instance, if you have a composition like this, it's not true that the resulting manifold will get an exotic structures. You have to be very careful about the order of the element. And indeed, there are some very. Yes, this is just to the diagram level, but the choices here must be done in a way that you know the common boundary and you know the correct order to do the procedure. Also, in the sense that, well, if I can just perform it, that has to be the order. So you have to take S3 times D4 or D4 times S3 to make the identifications at the matrix level.
But my point is that this is a 7 thing, but if I multiply by S1,
yeah. Yeah, exactly.
Then, my question is whether this can really be written or should be written as a more close to the traditional log term form with logs.
I see your point. Yeah, we can do this, but we indeed. Yes, I will be the one explicit example right now. Yeah, just let me just point out that in this kind of thing here, this FP2, so 2 minus 1 can be just obtained. So we can compose here. The choice of sign infinity, the choice of sign infinity has to be such that FP1 0. So let me just go back to what you were just saying, Ernesto, because then I will give you.
Let me tell you the motivation for my question.
Yeah, go ahead. Go ahead.
But I just want to know what all minimal structure you're working.
Mm-hmm.
What you're really doing in which Lego set.
Mm-hmm. Mm-hmm.
So this is the origin of my question.
Yeah, I see.
Kind of this nice small.
Yeah.
Well, everything can be achieved. Nice.
The minimum amount of data you want to know to be everything like definable. Mm-hmm. Mm-hmm. I see.
So if I can write it as a first order statement of blah blah blah, that kind of thing.
Yeah, written in first order logic, you mean?
This kind of thing.
Yeah. I never really thought about it, but yeah. Just let me, yeah.
But I think, yeah, you are building it with your hands. So yes, the answer is yes.
Okay, so just like yeah, the classical logarithmic transformations are able to be written in this minimality setting, and then we can do this analogously, because it's just a matter of determining which kind of matrix that we are, what is the correct frame to build logarithmic transformation. That's the question.
It looks like, and maybe it's true, you have these fractal torus that
exactly.
Maybe, but it would be nice if the torus was nice, and everything was nice, and so on and so forth.
Yeah, precisely. But then the point is that when we write like in this manner, depending on what we want to determine or not, then we can just write this S3, for instance, as the mesh product. So somehow you are like making some recursion to the classical logarithmic transformation, then choices which shall matter much more. And the complexity of the resulting manifolds from the logarithmic transformation shall be determined by some combinatorial geometric group theory. So it only ends up making this mesh, and you can become to the, like you are making a recursion procedure to rely on everything that's made on the classical logarithmic transformation aspect.
But when you do it like that, it seems a little bit puzzling that we would still have smooth structure. You're doing class C0, but you describe it like that.
It is possible, but I don't know if when we glue everything, how it shall work. Because the point is that spheres, unlike perhaps elliptic vibrations, are very low. In the sense that an exotic sphere differs from a classical sphere just by 1 point. 1 point alone. That's all. While in elliptic vibrations, you have the concept of nuclei that Hopf introduced, and everything that matters, every manifold obtained from logarithmic transformation from elliptic vibration is completely determined by the nuclei. And the boundary of the nuclei is the Briggs-Smart sphere. So it's more or less like all the possible decompositions in disks of exotic spheres or manifolds.
So to change my question a little bit, if I multiply the whole story by S1,
the next step, yeah.
Would the whole story be decided by actual complex structures? And then there is this Brouwer group that decides complex structure, and then this Brouwer group that decides smooth structure, and they should be more or less corresponding.
Yeah.
And then you said, well, it depends on 1 point, but some of the smooth structures, they depend on actual compactification and so on and so forth. So it seems to me that you just that's why you're doing it, and it works, it's fine. It would be nice if you were just a little bit more careful to keep it within the old minimal framework, which is not much help. It's all I'm saying.
Yeah, no, I will definitely take into account because this is just some bubbling ideas that we have been discussing for this one. Yes, since May there is not very long time. I just learned this duality stuff in May here, so we're just trying to get it. myself personally, I try to get acquainted with this. But something that Ludmil certainly already asked is about how it behaves under product. And perhaps this is possibly related to the kind of thing that you have in mind. And all we know is that if we take, for instance, two, let's just finish it. And so the point is that logarithmic transformations can be made in a very topological manner, and that's a precise point. And how is this related with classical logarithmic transformations? This is the last point that I want to remark, because here we have this for this tori and then classical vibrations, and here we have for something that's in a Zotki sphere or not. And what if we consider, and this is the last thing, and perhaps it will add some spice to the points of Ernesto, that is precisely. Let's consider a very classical elliptic vibration. This one here, we have S3 times S1, which base over S2. Hopf manifold, okay? Then let us construct this I hat here, S3 times S1 times S3 times S1, that goes to S2 times S2. So here we have an 8-dimensional object in the total space manifold, and yes, a 4-dimensional one. Looking to this kind of logarithmic transformations, only looking to disk decompositions, we can perform the two kinds of logarithmic transformations. How are these related? Meaning that if I obtain some manifold here, let's say x of some psi by this kind of generalized logarithmic transformation with blooms and straightened angles, can be this manifold obtained from performing classical logarithmic transformations on this factor and this factor.
The two at once together.
Exactly. And the answer is not always. And the answer is not always. It's not always like commutative or decomposable commutative. So in this point, the possible decompositions do depend on the way that you make the procedure. It's not diagonal at once. That's the point. It can be made upper triangular, but not diagonal at once. So all in all, the only resulting manifold that can be decoupled by making separate logarithmic transformation. Sometimes you can, yeah. But okay, this justifies it.
Well,
yeah, no, I see. Yes, and you can completely determine what kind of works or not. Sometimes look to the fundamental group level because of the presentation that you get by the amalgamation product. Because look here, this is just matrix multiplied
all the words.
Exactly. That's the point. The words of the presentation. Exactly. It's just a matter of deciding whether you can decompose, split, or unentangle the words. The words can be split like variation, what is this? Variable separation. Like you can decouple this, yeah. That logarithmic transformation should do something like the product becomes the sum in the sense of logarithm in the classical point of view, yeah. So after all of this, what I'm trying to say to you is that we are starting to look to this spherical stuff, and perhaps not only to this how this mirror symmetry became, but now looking to the more simple way of smooth structures and make some connections with geometric group theory, and it all was born here in May. And so I cannot wait to the next conference to bring new ideas and perhaps finish some old ones.
Yeah,
yeah, and I thank you very much for your attention. Thank you.